Captions in English. So this is the 10th video of chapter 7, and we will look at other ways to classify reactions by what atoms do. And so let's look at a video that summarizes this.
There are 5 major classes of chemical reactions. A synthesis reaction is when 2 or more substances combine to form a single product. In a decomposition reaction, a compound breaks down into 2 or more simpler substances. A single displacement reaction is when one element takes the place of another in a compound. In a double displacement reaction, the positive and negative portions of 2 ionic compounds interchange. A combustion reaction occurs when a substance rapidly combines with oxygen to form 1 or more oxides and releases energy.
So classifying chemical reactions by what atoms do. So this summarizes the 4 kinds of ways to classify by what atoms do. There is the synthesis or combination, where you have 2 reactants and you're making only 1 product. There is the decomposition, where you are having 1 reactant only and breaking it apart into 2 or more products. So decomposition and synthesis are opposite processes. Displacement or single displacement is usually how it is called. It's when you have an element plus a compound gives a different compound and a different element. So there has been an exchange of element in the compound. And a double displacement reaction is when you have 2 compounds and they exchange partners and become 2 new products. Note these are more generic categories, so pay attention to the patterns for these reactions for determining the type. So here you really need to watch what elements do to classify them as such. So let's go through each of them. First, synthesis reactions, also called combination reactions. In a synthesis reactions, 2 or more substances combine to make a more complex substance. So usually the key to recognize a synthesis reaction is that you have 2 or more reactants and they combine to make only 1 product. In this series of photographs, we see how sodium metal and chlorine gas are reacting together. And when they combine, a chemical reaction occurs that forms sodium chloride, NaCl. So you see you have 2 reactants and only 1 product. Decomposition reactions are the opposite of synthesis reactions because a complex substance breaks down to form 2 or more simpler substances. So you have 1 reactant and you're making 2 or more products. For example, when an electrical current is passed through water, the water undergoes a decomposition reaction to form hydrogen gas and oxygen gas. So the reaction is that you start with water liquid or liquid water, and you decompose it into hydrogen gas and oxygen gas using electricity. And you notice how the hydrogen gas is formed in one electrode and the oxygen gas is formed on the other electrode. And you can separate them and collect them separately. Another example of a decomposition reaction, LiHCO3, so lithium hydrogen carbonate or lithium bicarbonate. is a solid that you can decompose into lithium carbonate, Li2CO3, and water and carbon dioxide gas. So you see how you have only one reactant and you're forming two or more products. Single displacement reactions. In a displacement or single displacement reaction, one element displaces another in a compound. So they are of the form A plus BC gives B plus AC. For example, when metallic zinc is immersed in a solution of copper 2 chloride, the zinc atom displaces the copper in the solution. So that's the chemical equation that corresponds to this. So zinc as a solid, as a piece of metal, when it's placed in a copper chloride aqueous solution, zinc will take the place of the copper in the chloride compound. And you will have then copper displaced and becoming a metal solid. And then the zinc will be a cation now and binding to the chloride and making the zinc chloride. So that's a single displacement reaction. In a double displacement reaction, two elements or groups of elements in two different compounds exchange places to form two new compounds. So you start with two compounds and you end up with two different compounds. And there has been an exchange of partners, if you will. A double displacement reaction follows the general form of AB plus B plus CD gives AD plus BC, or CB, sorry. Because typically these are ionic compounds, and the first element in the formula is the cation, the second element is the anion. So you need to combine A with D because it's a cation with an anion, and then C is the cation with B the anion. And so that's how you would write their new formulas when they exchange partners. Example, NaCl, an aqueous solution, plus AgC2H3O2, another aqueous solution, make NaC2H3O2 plus AgCl solid. Notice how C2H3O2 is the acetate ion, and so we have silver acetate and sodium chloride. And so the sodium will take the place of the silver in the acetate compound. So now you see that it's sodium acetate, and then the silver will combine with the chloride, and it's AgCl. And it happens that AgCl is insoluble, so that's a solid. And so that's a precipitation reaction right there, because you have formation of a solid. And so the kinds of reactions that are double displacements are precipitation reaction, like the example above, acid-base reactions, and gas evolution reactions. All of these are typically double displacement reactions. So this summarizes how we can classify chemical reactions by what atoms do. They can be a synthesis, decomposition, single displacement, or double displacement. But when you have, the other way of classifying that was using a precipitation reaction, acid-base reactions, gas evolution reactions, and oxidation reduction reactions is a different way of classifying. And however, this way of classifying here is not, can be, also used at the same time as the previous way of classifying. So for example, oxidation reduction reactions, they can take all forms. Here you see that they can be synthesis reactions if the reactant are elements. So synthesis reactions are not always redox reactions. They are only a redox reaction if what is said in the parentheses is true. So here, a synthesis reactions is an oxidation reduction reaction if the reactants are elements. Decomposition reactions are also oxidation reduction reactions if the products are elements. And then single displacement reactions are always oxidation reduction reaction. And combustion are also always oxidation reduction reactions because they are a subtype. It's when you have the addition of oxygen. So that means there are multiple ways of classifying a reaction. You can use the first type of classifying or this new type here of synthesis, decomposition, single displacement or double displacement. So let's practice that. And first, let's look at how we will use acronyms here to name each type of reaction. So P will stand for precipitation, AB for acid-base, G for gas evolution, OR for oxidation reduction, C for combustion, S for synthesis or combination, but S for synthesis is easier to remember, D for decomposition, SD for single displacement, and DD for double displacement. So let's look at examples of reactions here and find all the ways that we can classify them. And we will use the key that we introduced in this slide. So the first reaction has calcium sulfate as a solid becomes calcium oxide as a solid and SO3 gas. So here you have only one reactant and you're making two products. So this is typical of a decomposition reaction. And even though we are making a gas, this is not a gas evolution reaction because you're not starting with solutions. Gas evolution reactions need to start with aqueous solutions. I think that's the only way I can find for this one. It's a decomposition. 2Na plus O2 gives Na2O2. So we can see here we have the addition of oxygen. Oxygen is one of the reactants, so that implies that it's a combustion reaction. Let's look at the state of oxidation. Here we have sodium and oxygen, both in their natural state, so with oxidation states of 0. And we can see that when they become Na2O2, the Na plus is becoming, an anion of +1. And so the oxygen, each of the oxygen will be -1. So 2 Na plus 2 oxygen minus will make this a neutral formula. So this confirms that it's a oxidation reduction reaction. So it's an oxidation reduction reaction because sodium, for example, goes from its 0 oxidation state to a +1 oxidation state. Oxygen goes from its natural state to a -1 ion. So it's a combustion because we have oxygen as the reactant. And it's a synthesis as well because we are making only one product. You see that you're adding two elements and making one product. That's the key to recognize a synthesis. So S for synthesis. Next example, we're given only the reactant there. H2SO4, the sulfuric acid, and BaOH 2 times, both in aqueous solutions. So we need to find the product. Here we can see that we have an acid and BaOH is actually a base. So that's an acid-base reaction. And typically these are double displacement reactions where you have an exchange of ions. And we can see that the hydroxide in the barium hydroxide here can combine with the H plus from the acid. And so H plus plus OH minus makes water. So we'll make water. And then the barium 2 plus will combine with the sulfate 2 minus. And that's going to be BaSO4 because 2 plus 2 minus, they cancel out. So we need to decide if BaSO4 is aqueous or not. And so let's look at the table of solubility rules for that. So we have BaSO4. We have SO4, the sulfate listed among the mostly soluble compound. Let's look at the exceptions. When SO4 2 minus pairs with strontium 2 plus, barium 2 plus, Pb2 plus or calcium 2 plus, the compound is insoluble. And here we have barium 2 plus, so that means it's insoluble. So that's why we had the S in the equation. So this justifies the fact that we have S after BaSO4. That's a solid. So we need to balance this equation. We can see that the 2 hydroxide ion and the 2 H plus ion will make 2 molecules of water. And then the BaSO4 is already balanced. So to summarize, we have an acid-base reaction. H2SO4 is the acid, BaOH2 times is the base. We are forming water plus a salt. But the salt is insoluble, so that's also a precipitation reaction. And both acid-base and precipitation reactions are double displacement. And the way we find the product for these equations is expressly because we recognize them as double displacement reactions. Example D. So we have 2 aluminum metal plus Fe2O3 solid gives Al2O3 solid plus 2 iron as a solid. We can see we have aluminum as a solid metal and iron as a solid metal, which means they have an oxidation state of 0 there. We see that they are both elements, and then they are, they are accompanied by a compound. Let's find the charge on the elements in the compound. So Fe2O3, if you undo the formula, you find that Fe is 3 plus and O is negative 2. Because if you undo the crisscross trick, you retrieve that. So that's the charges of the ions in Fe2O3. And Al2O3 is the same. We have also 3 positive charges on the aluminium and 2 negative charges on the oxide. And that's, predictable ions. So this is expected to be this way. So we can see that aluminum goes from a natural state of 0 to 3 plus cation. And then the iron goes from 3 plus state to a 0 state. So this is definitely an oxidation reduction reaction. We can also recognize this as a single displacement. We can see that aluminum has replaced iron in the oxide. You can see that if you change the iron into aluminum, you get the same oxide. And then iron now is in its elemental state as a metal. So single displacement and oxidation reduction reaction. Last example, we have H2SO4, the sulfuric acid, plus NaHCO3. Here we can recognize that we will need to exchange partners again. NaHCO3 is a base, even though it's not part of the base you've learned in this chapter, but that's a base. And so HCO3 can combine with the H+. HCO3 -1 is the bicarbonate ion or the hydrogen carbonate ion. It combines with the H+ to form H2CO3. And then the Na+ will combine with the SO4, and it's going to be Na2 because you need 2 sodium with 1 positive charge each to combine with the sulfate, which has 2 negative charges. So Na2SO4 is the salt there. We know that H2CO3 is aqueous and it's actually unstable, it decomposes. And Na2SO4, from the solubility rules, we know that all alkali metal make Ores soluble compound, and sulfate are mostly solubles also. But here the sodium makes it an aqueous solution. So that's why here it's aqueous for Na2SO4. Let's balance the equation now. So from the bicarbonate ion HCO3, we have made H2CO3 with the H+. So that's balanced, but here we have 2 sodium in the sulfate on the right side and only 1 sodium on the left side. So we need 2 sodium on the left to make it 2 sodium on both sides. But now that we have 2 bicarbonates, they will make 2 carbonic acid. H2CO3 is the carbonic acid. And we see that those 2 bicarbonates will combine with the 2 H plus from the sulfuric acid and make the carbonic acid. So we said that H2CO3 is unstable. It's decomposing, and it's decomposing into H2O and CO2. So from the 2 H2CO3, we actually get 2 H2O molecules and 2 carbon dioxide molecules. We can see that it's still balanced this way. So ways of classifying this are we did double displacement to find out the formulas of the product. We see that it's a gas evolution reaction. And I would add that it's also an acid-base reaction, but that's not of the form that we are used to see in this chapter. So that's why it's not listed there. But it's also an acid-base reaction. So gas evolution reaction and double displacement.